Okay, welcome to Chapter 2.3, 3.3, and 4.1, Conservative Forces, or work done by forces that are internal to the system, or not external. So, by the end of this online lecture, you should understand or know the definition of kinetic energy, a definition for potential energy, a definition for a conservative force or an internal force. How to determine if a force is conservative or internal to the system, and an introduction into what are called equal potential lines. So let's get started. All right, so we're going to start off right here where we get some force that's a function of x is equal to its mass times the second derivative of the position. And if we do that, we can rewrite the second derivative of position as the first derivative of the velocity. And if I multiply by this factor of 1, dx over dx, and rearrange it in this manner, I get what looks like to be the velocity times the derivative of the velocity with respect to position. And so if I use that, I can take that and I can plug it back into my force equation and write it this way, or Newton's second law, and write it that way. And if I write it that way, what we can do is rewrite it this way. And if I take the derivative of this with respect to x, I should get this right back. And then the mass and 2 are constant. And if I bring it inside, that defines what is the kinetic energy. So T in this course will represent the kinetic energy, not K. So doing that, this expression says the change in kinetic energy with respect to position should equal to the force in the x direction. Or this is a separable differential equation, so if I separate it and integrate both sides, I get this. So what is this integral right here? That ends up being the work done by the external forces on the system. So the work done by the external forces on the system is equal to the change in kinetic energy of the system. Something that you should remember from Physics 153. So if we take this a step farther, what we have is our definition here. And what I'm going to say is I'm going to define the force as being the negative derivative of position with respect to this new function called v of x. And that new function is going to be called the potential. If that is true, I can plug it back into here. And then the integral exchanges this, and then I can still integrate both sides, and what I get is this. Now, if I put all the initial on one side and all the final on the other, I get this expression, and this expression is a constant, and we call this the total energy of the system. So now that I know that the total energy system is equal to its kinetic energy plus its potential energy, this brings an idea called equal potential lines. And what are equal potential lines? Well, equal potential lines are lines where the potential on these lines are always equal, and they look like this. You might have been exposed to this. These are also called contour lines. So this is a map, and these lines right here show the lines of constant height. And we could claim these are lines of constant gravitational potential, or constant lines of gravitational potential energy. And we can consider these equal potential lines, because on this whole line, the potential energy, if you stay on this line, is always going to be the same. It's not going to change. And over here, you might have seen this in 163. These are electric equal potential lines. And these are lines of constant electric potential. And if you stay on that line, you have the same potential. And these give us the idea of lines of constant potential, or what we refer to as equal potential lines. And then we can use this because the whole idea of a force is the change in potential between these two lines. There's got to be a force in order to change the potential from one side to the other. All right, so basically it comes down to this idea of conservation of energy. And you could rewrite this in this manner and then rewrite the kinetic energy in terms of the definition of kinetic energy. And then what we can do is solve for the velocity, and you get this expression. And I know the velocity is the derivative with respect to position, and now I can rearrange this and integrate both sides, and I can claim that the time it takes to travel from one point x to another point x is equivalent to this integral. And this would allow you to calculate the period of oscillation of a system if you wanted to, especially if you knew the potential energy of that object and the mass of that object. And so on and so forth. You could do something like that if we had to. All right, so let's look. We've done a lot of work on harmonic systems or simple harmonic oscillators or damped harmonic oscillators. We can also do this in do an energy aspect to this, and the idea here is that we want to find the work done by an external force. So we have our mass here at some equilibrium position E0, and then we're going to move the mass to some position X. And in order to do this, the spring on the system, there's a force of minus kx, and so in order for you to move it, you have to apply an equivalent force in the opposite direction, or a positive ks force, and that is our external force. And if we move it very slowly as we go out, then we don't add that much kinetic energy to the system, and we can figure out what the work we should do by plugging in the external force that we're going to use here, and then integrating over the distance we take it, and that gives us 1/2 kx, and this gives us a way of determining the potential energy of a harmonic system. So we have both the kinetic energy and the potential energy. It should be equal to the total energy of the system. And then if we know that, we can use this information to help us figure out some more information about our oscillating system here. Just another way of showing you how to use energies to help you solve a problem. So the way this textbook talks about it, they talk about conservative and non-conservative forces. But as we've explained it in 153 and 163, basically we're looking for internal forces that do work on the system, and if they are doing work on the system, that will give you a potential energy term. So how do we find these conservative forces or non-conservative forces? Well, the idea goes like this. If we have some object at point A and I want to move it to point B, I can choose any path to get it there. I'm going to choose this black path, and then go along this black path in this direction of the arrow, and that little arrow denotes an infinitesimal section of this path, and we usually call that dr. And then I come back from B along this other path, and again, it's a very elaborate other path, but it can be any path. It doesn't have to be this one, it can be another one, it could be a straight line. And I go along in the direction indicated by my infinitesimal little sections of this path that we call dr. And if I try to calculate the work done going from location A, or location 1, to another spot called location 1 again, so I start from 1, I go to B and come back to A again, which I'm calling location 1, the work done by the internal forces should be 0. If that's true, then we have a conservative force, and we have an internal force, or an internal force as we call it. And the way we look at that is that this is a closed path integral where you travel along some closed path that starts at one point and comes back to that same point. And if you do this and you have this conservative force, that is the internal force, then the work done by this force has to be zero. And that is the definition if a force is conservative, or if the force is internal to the system. That's got to be true. So if we apply a vector algebra theorem called Stokes' theorem, which states is if I have this closed path integral, and then instead of going along the path, I can expand it into an area integral across the surface that is enclosed by this path, and then I integrate the curl of this force, I should get the same answer by applying Stokes' theorem. So we know that if this force is conservative or internal, this has to be zero. So that's going to make this have to be zero. Well, the only way this is going to be zero is the thing you're integrating over is going to be zero. So this is n hat is a normal vector, normal to the area you're going to. And the way you figure out which way it points is you use the right-hand rule, and you take your fingers and you point them along the direction that this dr is going along the path, and as you curl them around, your thumb points in the direction of n hat. We can do this in class. And then you integrate across some infinitesimal area element that is enclosed by your path, or in this picture, it's this area here, or this area here. It's all enclosed by our path. And if this integral is zero, this has to be zero. The only way this is going to be zero is that if this term is zero. And so this is how we find out if our force is conservative or internal, is if we take the curl of our force, and that curl is zero, we have an internal force, or a conservative force. So that is a key thing that you guys need to remember for this. So, in the end, you should know how we found the kinetic energy of a system. You should know how we define the potential energy of the system. Now, this is a one-dimensional one, just over x, or the space x. It doesn't have to be x, it could just be r. This would be br. But if we wanted to do three-dimensional, the way we write it is that if the force is equal to the negative gradient of some potential, if that is true, the force has to be conservative or internal to the system, because the curl of a gradient is always zero, if you remember your calculus 3. And then the other definition is the work done by this internal force around some closed path. That if that's equal to zero, we know that force is internal or conservative. And then the other way to look at it is you can take the curl of that force, and if we're using this definition, then this curl will always be zero. All right, and then the fact of this thing called equal potential lines is that you can create a line where every value of the potential along that line is the same value. And then we can create these, what we call contour plots of these potentials, and they can be useful for helping us figure out information about the force, which way the force should be pointing, whether the force is a maximum there or not, because remember the force is proportional to the slope or the change in those potentials over some position change. Alright, so that finishes this lecture on conservative forces or internal forces. I'll see you in class. Bye.